Today we're going to cover allowable stress. So recall the main equations here. Fs, the factor of safety, equals the force of failure divided by force allow, or stress failure divided by stress allow. And we also, from there, have another equation where A, the area, equals force divided by stress, or stress equals force divided by area. So those are like the four main equations, pretty simple. This is quite a lengthy problem, but it's not that difficult. So the rigid bar AB is supported by a steel rod AC having diameter of 20 millimeters and an aluminum block down here having a cross-sectional area of 1800 millimeters squared. The diameter of pins A and C are 18 millimeters. They are subjected to single shear. If the failure stress for the steel and aluminum is 680 and 70 megapascals, and the failure shear stress for each pin is 900 megapascals, determine the largest load P that can be applied to the bar, applying a factor of safety of 2. Okay, so basically what all of that says is, given these allowable restraints, given these failure restraints and the factor of safety, what is our P load so that our structure does not fail? So basically I extracted everything from the passage into readable information. The most important thing is to convert diameters to radius right away and convert millimeters to meters right away. If you don't know how to convert millimeters squared to meters squared, I recommend you look it up and figure that out. So here we go. This is all the information that we have. So I drew out a free body diagram. I have the P load, which I'm trying to find, some unknown FAC reaction force caused by this rod, and some unknown FB force caused by the aluminum block. So here the process we're going to follow is we're going to find the allowable stresses. From the allowable stress we're going to find the allowable forces, and from those forces we're going to find our P load, or the max load that we can have without failing. So typically we're used to working the other way around, finding the forces and then from the forces finding the stress. So here we're just working backwards. And it's not difficult as long as you keep track of all of the knowns and unknowns. So first we're going to use what we're given. So they gave us all of these failure stresses, the factor of safety, and we know the equations that relate them. So from those knowns and the equation, we're going to find the allowed stress, the allowed normal stress, and the allowed shear stress. So I do it for the steel. Steel allow equals fail divided by factor of safety. I do it for the aluminum block, and I do it for the pins which have a shear allow, right? So I end up with 340 megapascals, 350 megapascal, or 35 megapascals, and 450 megapascals. And remember, megapascal is a Newton per meter squared, but mega is times 10 to the 6th. So this is like 450 times 10 to the 5th or 10 to the 6th pascals. Sorry, 450 times 10 to the 6th pascals. Okay, so now we have found our allowable stresses, right? From our allowable stresses, we have these equations where stress allowed equals force divided by area, or the same thing, shear divided by area. So we rearrange those equations and we end up with force equals allowed stress times area. So from that equation and these knowns that we just found, we can find all of the forces. So FAC caused by the rod, FB caused by the aluminum block, and we have a second FAC which is caused by the shear in the pins. So FAC equals allowable stress 340 times pi r squared, and all of the diameters and areas we were given in the initial statement, so I just use that. I end up with 106.8 kilonewtons. For the aluminum block, 35 megapascals times the given area is 63 kilonewtons. And then for the pin, so the pins have some shear force, right? And that shear force is the same thing as FAC. So we have two different values of FAC. two potentially different values of FAC. This one is caused by the rod itself, whereas this one is caused by the pins. So 450 times pi r squared equals 114.5 kilonewtons. So we have just found the values of the forces in our diagram, and these are allowable forces. So these are forces at which our structure will not fail. So allowable forces. Once we have our allowable forces, we want to find a relationship between allowable forces and P so that we can find P allowable. So I get these relationships by taking the moment. So first I pin my structure at point B. When I pin it, I have FAC and P causing a moment. So negative FAC times 2 meters plus P times 1.25 meters equals 0. So I get this equation or this relationship where P equals 2 FAC divided by 1.25. I do the same thing. I pin the beam at point A and do some of the moments. So negative P times 0.75 plus FB times 2 meters equals 0. So here's my second relationship where P equals 2FB divided by 0.75. So now I have a relationship for P and FAC and P and FB. And I just found what FAC and FB were previously, right? So I just found my allowable forces. FAC has 2 potential allowable forces and FB has only 1. And I have these 2 equations that relate those 2 things to P. So starting with the first equation, P equals 2 FAC divided by 1.25, approaching it from the steel rod, where FAC is 106.8, I plug that in and I end up with 171 kilonewtons for P. Then I approach it from pin A or pin C, where FAC was 114.5 kilonewtons. So I end up with P equals 183 kilonewtons. And then I use the second equation in terms of FB for the aluminum block. I plug in the 63 kilonewtons for FB and I end up with 168 kilonewtons. So you're thinking, I have 3 different values for P, which one is the correct answer? So they ask you for the maximum load that P can be before the structure fails. So if we look at aluminum block, the structure will fail if P is 168 kilonewtons. So the entire structure will fail based on P because the allowable stress at the aluminum block is kind of a limiting factor here. For the steel rod, it's 171, and for the pin, it's 183. So even though these are bigger and you might think, oh my gosh, I need to use the biggest value. No, the allowable force that P can be is 168 kilonewtons, because after this point, everything will fail, right? So 168 is the highest that my force can be, because if my structure fails due to the aluminum block, it doesn't matter if I use a higher value because it's already failed. So P allowable, or the largest load that I can have at P, is 168 kilonewtons. I hope that makes some sense.